Today's video is about what are called the gas laws, and there's three main gas laws that you should be familiar with in terms of chemistry. All three of them deal with changing one condition of the gases and how it affects the other gases. Now, a lot of times these questions are not math questions, they're just thinking questions. So, in terms of, for example, the first one here, Boyle's Law. Boyle's Law tells us, and again, there's always a good way to think about these. So in terms of Boyle's Law, it tells us that the pressure is inversely proportional to the volume. So that means that if you decrease the volume of a container, the pressure is going to go up, okay? So Boyle's Law basically says when the volume goes down, the pressure goes up, okay? And I think about that in terms of like taking a water bottle and you squeeze it. Remember how you can shoot the lid off of the water bottle? That's because when you squeeze that water bottle and you decrease the volume, there's less room in that container. Okay, and this is the part where if it's not a math question, it's going to be a can you explain it question. Okay, so why does that happen? Why, when you squeeze that water bottle, does the pressure inside go up? Because the gas particles collide with each other and with the walls of the container more frequently. Okay, that's the key right there. So they're colliding with each other, and more importantly, they're colliding with the walls of the container more frequently. That's how you want to say that. And if, again, that's what pressure is how many times those particles hit the walls of the container. So if they're hitting the walls of the container more frequently, that makes the pressure go up. Okay, so that's Boyle's Law. Now, there's a mathematical version of that. Don't worry about that yet. We'll get there in just a second. Okay, Charles' Law, again, and you don't need to remember the names, tells you that if you raise the temperature, so temperature goes up, then the volume also goes up. So notice up here with volume and pressure, that is an inverse relationship, which means when one goes up, the other one goes down. This one here is called a direct relationship, which means that when one goes up, the other one goes up as well. Okay, now, why does that happen? And again, let's think about this in terms of, I always think about when I put a balloon in a freezer. If I put a balloon in the freezer, the opposite of this here happens. I'm lowering the temperature, and when you lower the temperature, what does that do to the volume? The volume obviously is going to go down, okay? So, temperature goes up, volume goes up. Temperature goes down, volume goes down. That's a direct relationship. So why does that happen? Because when you increase the temperature, we talked about this with the kinetic molecular theory. What's the one thing that temperature affects? It affects the kinetic energy. So when the temperature goes up, the gas particles have more kinetic energy, and that means that they collide again like the first one. They collide with each other and the walls of the container. Now there's two things though, not just more frequently, but with more force as well. Okay, so if they're hitting the walls of the container more often and with more force, and again, for Charles' Law to work, notice it does say at constant pressure. That means the pressure can't change. Same thing up here with Boyle's Law. It means constant temperature, which means if the temperature changes, you're not using Boyle's Law. If the pressure changes, you're not using Charles' Law. Okay, so if the pressure remains constant and the particles, the gas particles, are hitting the walls of the container with more force and more often, more frequently, that's going to cause the pressure, or that's going to make the volume go up. Okay? And then the third one here, this is actually a French guy named Guy Lussac. This is called Guy Lussac's Law, and I'm probably pronouncing that wrong, sorry. Okay? Is actually a kind of a combination of those two. This one involves pressure and temperature. So here, when the volume is constant, when again the temperature goes up, and again, let's say it's a rigid container, it's not a balloon, it's not a water bottle, it's a container that the volume can't change in, then the pressure also has to go up, okay? So that is also a direct relationship. And again, why does that happen? And again, the names of the laws do not matter. It's you understanding that when this happens, why does that happen? Why does this happen? Okay, why does the pressure go up when the temperature goes up? Because it's when the temperature of the gas is increased, again, the particles have more kinetic energy, and then they collide with each other and the walls of the container, again, with more force and more frequently. The exact same reasoning with Charles' law, okay? Nothing different there, other than in one case, you're in a rigid container where the container can't get any bigger or smaller, then the Gay-Lussac's law is going to come into play, okay? If you're in a balloon or something that can change its volume, then Charles' law will apply. Now, this used to be, all three of those put together make the combined gas law, okay? And so I don't want you to remember each one individually. I simply want you to remember this law right here. So this used to be on the equation sheet, and they still do ask problems about it. So, and I don't know what to say. I don't know why they keep putting some equations on and taking other ones off. But really what you need to understand is, let's say in the problem they tell you that the temperature is constant. Well, what do? You take temperature out, and then you just have P1V1 equals P2V2. And that's Boyle's law. Again, the names don't matter. What if they tell you that the volume's constant? Anytime something is constant or that it doesn't change, you take it out. And then you have P1 over T1 equals P2 over T2. So P1 over T1 equals P2 over T2. And again, that's the Gay-Lussac's law there. Okay? And then again, obviously, if the pressure is constant, so the pressure isn't going to change, now you have Charles' law, which is the V1 over T1 equals V2 over T2. So there's all three of those laws in a very nice, easy P1, V1. And what if nothing stays constant? Well, then you do use the entire combined gas law. But typically, one of those three will remain constant, and then you end up using one of these equations. Okay, in terms of pressure, what unit do you need to use? We talked about atmospheres, we talked about millimeters of mercury, we talked about torr. In this equation, it doesn't matter. They just have to be the same unit. Okay, pressure can, if this pressure is in atmospheres and this pressure is in millimeters of mercury, then you have to make them the same. It doesn't matter which one, but you have to make them the same. Okay, volume, the same thing. Volume will probably be in milliliters or liters. Again, it doesn't matter for this equation. It's going to matter here in our next equation, but for this equation, it doesn't. Okay, the only thing that really matters is the units is temperature. Okay, like when we talked about with the kinetic molecular theory, the temperature must always, always, always be in Kelvin. Even if in the problem they give you the temperature in Celsius, and then they ask you for the answer in Celsius, when you do the math, when you do this problem right here, or this equation, or this equation, the temperature must be in Kelvin. Don't ever, ever, ever use a temperature in Celsius. Okay? As soon as no matter what the problem is, as soon as I see a temperature in Celsius, I immediately cross it out and I change it to Kelvin. And then I never, ever have a problem with temperatures. So as soon as you see a temperature on a paper, even if it says the temperature is constant at 25 degrees Celsius, just cross out 25 and write 298. Okay? Just in case it comes up at a later point in the problem, it might say, well, the temperature is now changed from 25 degrees Celsius to 45 or whatever. Okay, then you're going to have to use the temperature, and it's going to have to be in Kelvin. So like I just wrote up there, there's Boyle's law right there. Again, the names don't matter. There's Charles' law. Again, oh, jeez, talk about some terrible editing there. The pressure must not be in Kelvin. The temperature. Hopefully you caught that before I did. Holy cow. Okay, so the temperature must be in Kelvin, something I need to change clearly in the notes. Okay, when the volume is constant, you just remove the volume and you get this equation again. Not only must you be able to solve problems, so you have to be able to do the math, but you also must be able to explain, again, those things I underlined in the explanation above, those italicized parts, that's the important part.